Good morning. Morning, everybody, for this fourth lecture of the second week of the Intelligent Systems course. Sort of the home straight of the second week and the home straight of the subject of how to represent knowledge. And today we're talking about, this is not working if I don't put this in, so let me simply do this first. So today is about probability and uncertainty. And basically the point is that we very often, as we have already encountered in Schnapsen, that we don't have perfect information. We can't model things with a crisp modeling paradigm, such as a propositional or first order logic, because things are unspecified or incomplete, uncertain or vaguely described. Things might be inconsistent. So the beautiful theory about the logical systems that I described in the first three lectures of this week, they very often don't work in practice. That doesn't mean that they are not useful. So I think that it makes a lot of sense to model strategies, for example, to help you guide through the decision space as we now do in Schnapsen. I think this is really can be extremely useful. Even if you do not know the cards of your opponents, you can still reason over what might be a good strategy or not. But logic itself is not sufficient for these problems. And we had one of the bots that you have seen perform some kind of sampling over data. But this is not a very explicit way of reasoning, or you can't really do much about this information either. So people, of course, have thought about ways of how can we model vague information, so such as being tall, being small, and these kind of things. And people have thought about uncertainty. So I know probably that the wind will ease later today. There's no certainty that this will happen, but there is a high probability that it will happen. And this is obviously something that's very important if you want to program an intelligent agent, because these systems have to deal with these kind of uncertainty in complex environments. So first, before we get into this, it's important to understand the difference between uncertainty and vagueness. So a glass is full 50%. So what does it mean? There are two different ways of seeing this. The one is to say, I have a glass that is half full, or that I'm not sure whether the glass is full or not. So in this sense, here we talk about two events, namely I have a full glass or I have an empty glass, and the probability that the glass is full is 50%. So in these cases, so half of my events have a full glass, half of them have an empty glass, so 50%, 0.5 probability that the glass is full when I pick one randomly. That's completely different from the point where you say, I have one glass and it's half filled. And then the question is this really a truly half? So do we really have a glass of 0.2 centiliters or 2 centiliters, and there is exactly 1 centiliter in it? So that would be an attempt to make this vague notion crisp. But it's very important that you really understand the difference between these two concepts, even though they, in a way, use the same statistical approach of saying, okay, we have some sort of 50% notion of fullness, and that is either the chance of being full or the amount of water in it. Two completely different things. So here we talk about vagueness. It's more or less half full. And here we talk about uncertainty. We're not sure which of the two we pick, if we pick the one which is full or we pick the one that's empty. And that's basically what we're going to do today. We talk about vagueness as a concept and formalisms, logical formalisms that deal with this vagueness. How to represent it, how to reason and with uncertainties is then the major part. We will need that also for next week when we get into the learning, because probabilities are underlying one of the simplest and most intuitive learning methods that I'm going to present on Monday. And then if there is time, otherwise I do it on Monday, I talk about the exam and about the final report, because there is sort of, far enough to have maybe more benefit from an explanation of that. So remember that the model theory that I was talking about the last 3 days, so the idea of grounding the notion of truth or attainment on the basis of the notion of a model, is often based on set theory. So if you have in propositional logic, we interpret the elements as true or false, but we can in first order logic, for example, interpret objects, and then if we relate objects, we get into the realm of set theory. So we describe, for example, the set of all tall men. So X is a man is one property, and the other one is that we have a length of, and then the problem, of course, occurs. At what point in size do we consider someone to be a tall man? And if I would ask this question in China, it might be a different question to if I pose it in the south of Italy or pose it here. And if you have, for example, the tall man in the basketball team, they are something else than the tall man in this class. So I don't think anybody would qualify as a tall basketball player in this classroom. You looking to the back, is there anybody you have in mind? Okay, anyway. Okay, good. Let's discuss it outside class. So basically, this is a notion that has a context, but it's also a notion that where we can put a number to it and say, okay, if you're bigger than 190, then you're tall, and if you are 198.5, then you are sort of medium. These crisp notions of propositional logic and first order logic, they don't really work on this. So basically what you do in fuzzy logic is that you assign to each of the propositions not a value, but a fuzzy function. And then you apply fuzzy set theory on the basis of a degree of belonging to the class of tall things. And that's the basic strategy at the moment. The main formalism to deal with vague terms. So how does it work? We have fuzzy sets as sort of the semantics of fuzzy logics, where you have a universe which consists of objects, and then we have for each of the objects in the set, we have a function that ranges from 0 to 1. Don't confuse this with probabilities, which is also mapping from value 0 to 1, but here it's a completely different meaning. And the notion of an element X in this universe is interpreted to be true to a certain degree. So X is a member of the class of, for example, tall people to a degree Y. Or it holds with a certain certainty of Y. And we have the two extreme cases, namely that X is Y, and then we say it certainly is a member of A. So if you have the value tall 1, then you're sure that nobody will dispute that you are tall. And if the value is 0, then you're certainly not a member of A. And basically what you want to do now is to find an algebra, a way of calculating with this notion based on this semantics of assigning a function to the object in the domain. So here would, for example, be a representation of the notion of a membership function of the fuzzy set of tall men. So you see it's not a yes or no value anymore, but is if you have a certain size, which is represented on the x-axis, then you would probably say that if someone is 120, a man of 120 is generally considered to be small, not tall, I would say, so very low f of x value. And then there is a transition up to the moment where you say, oh yeah, somebody from more than 2 meters is really considered tall, even in whatever context you might choose. And these functions, they can somehow be learned and trained from training sets. So they are approximated by knowledge that people have agreed on. So this was increasing notion. So it is monotonic. So the more the taller you get, the more you belong to the class of tall people. And there are some of these concepts such as tall, old, heavy, long, and so forth. But there's also other shapes, so approximate notions, where you might have the peak somewhere in the middle, the maximum, and then on both sides the shape goes down again. So medium-sized is an example. So you would have a medium-sized city of in the Netherlands, for example, of 80,000 people. And then if you have 500 people in your village, then it's definitely not a medium-sized city. And Amsterdam with 1 million would also not be a medium-sized city. So this is a different shape, which more used to approximate a concept as opposed to one which is one that describes an increasing notion, such as length or height and so forth. Then there are terms that help us sort of modify a fuzzy notion. So, for example, if we have a fuzzy notion of being tall, and then you have an alternative, a modifier that says very tall, then you would expect the function to be just a shift from the left to the right, or from the right to the left, but in principle keep the same shape, because it's just a modifier of the function by some constant or maybe some complex value. So now we have the ambition, the intuition, but what you want to really do with this is, of course, an algebra where you can do calculations on, and for that we need operators that are formally grounded in the semantics. And these operators that you have, they are, in this fuzzy set theory, they are very similar to the ones in normal set theory. You want to have a notion of a complement, you want to have a notion of union, notion of an intersection, and notion of a subset. And now the question is, of course, what does it really mean? In the complement notion, you just take the one off the value of the complement. So that would be if the not tall example, you would say that if someone is not tall to a degree of 0.3, you want him to be tall to a degree of 0.7. So 1 minus the 0.3. That's a pretty sort of natural notion. If you do the union, then you just calculate the maximum of two different values. If you want the intersection, you take the minimum of the two different values. And the subset is just this is a subset if the function is always below the function of the other value. So if you have small tall people and very tall people, then they are always to a degree taller than they are to. Sorry, this would be the A would be the very tall people, B would be the tall people, and then everybody who is a very tall person would be also a tall person, but there would be more people, so you would have a higher F value. And taking the union and the intersection is also a very sort of natural way of thinking about things, because, for example, if you want to look at the people who are tall or beautiful, then basically you look for the maximum value of them being beautiful or them being tall, because it doesn't really matter which of the two things you take, as long as they are as good as possible in one of these two different fuzzy concepts. And the same, very similar for intersection. So basically, if you have two fuzzy functions to describe a concept A and a concept B, and the one has the shape of an approximation and the other one has this sort of more strange shape, then the union of the two is just to take the maximum of the two. So you just take the upper a line, so that's basically this blue one up to here, then you take the red one up to here, and then you take the blue one again, which gives you this function. So basically we have a compositional semantics for the union operator, such that the union, the fuzzy value, the fuzzy function of the union of two concepts is defined by the individual functions just by taking the maximum value per possible x. For the intersection, it's the opposite. You start, you always take the minimum, so you start on the red one in the left-hand corner, and then you take the blue one up to this point and you go down again. So that gives you this, this shape for the intersection of the two fuzzy concepts A and B, the intersection of the two. So now if we have a logic that describes some concepts in given a fuzzy semantics, then basically we get a logical representation language that comes with this semantics in this space of fuzzy sets, and it's exactly the kind of logical operators that we have seen in propositional logic, but now they're interpreted in a different way, because they are not interpreted as as true or false, but they are interpreted as a value between 0 and 1, and the operators, the interpretation of a complex operator such as disjunction is the maximum, the interpretation of the conjunction is the minimum, exactly the same way as I just had on the fuzzy set theory side, which is the semantics of the whole thing. So here we are talking now about the syntax of my language, which is the same as the one in propositional logic, but now the interpretation is in a fuzzy way. So different semantics to the same language, basically. And the semantics for this fuzzy propositional logic appeared already 100 years ago, so it's a very old concept. But this is it's a very useful way to describe and reason about vague concepts or approximations of concepts. So if we restrict ourselves to the propositional operators, then we have exactly the same syntactic language, the same acceptable and legal sentences, but we give it a different semantics, give it a different meaning. And this meaning is dependent on the interpretation, so a function of one of the propositional values. We can extend this a bit by things that are possible in these fuzzy sets, so we can do these modifiers, so where we sort of shift the function. That's something that obviously isn't in the notion of propositional logic, but sort of that's makes the whole fuzzy logic maybe more powerful if we add additional operators. One of them is fuzzy composition that I'm going to talk about in a minute, because we can do more than just do fuzzy propositions. So we can say tall, and then we give it a function. But we can also say that two objects are in a relation that is defined by a function, by a fuzzy function. So someone being tall, so approximately equal, so two terms are approximately equal, is a function that is applied to a relation, or close to, much larger than, and so forth. And we can also model this given the fuzzy set theory and give it a fuzzy semantics-based meaning. So how does it work? We have a relation R, which is a subset of the Cartesian product between two sets, and we have another relation which is another subset. So basically what this says is that we have a function that goes from a relation that relates object from a class X and a class Y, and we have a relation that relates objects from the set Y and the set Z. And if you compose these two, you have this small circle. If you compose these two, then basically you have a relation between an object in the first set and the third of the set. So it's a composition of relations. An example would be if you combine the father relation with the brother relation, so the brother of my father, you get a new relation, which is the uncle relation. So the uncle is a composition of brother and father in the uncle. Basically, if I go from a class X of people to a class Y of people via the brother relation, and then I go from Y to the Z of the brother and the father relation, then I would now with the uncle relation, I would go from the first class of people to the third class of people. And classically, this is basically two things are in the composition. If there exists a third element in the middle, which is in a relation with the first relation and the second relation. So if you think of the uncle and father example, then this one would be the uncle relation, which would be the first to take the father. No, it has to be the other one. The brother, and it's something has to be in the father relation, and it then has to be in the brother relation. Yeah. So let's R be the father relation and S be the brother relation. So we need someone to be the father. So that would be the Y. That would be my father, and then this father has to be in a brother relation in order to satisfy this. That my uncle is in an uncle relation with me. So this doesn't work. Of course, we have to translate this now into the fuzzy relation. And the idea is basically this, that you look at the degree to which someone would be my father. It's not a very good example if I transfer it to the father relation because that's usually quite well determined. And then the brother relation, and you just take the minimum one of the first one and maximize it over the second one. So how does it look in an example? So if we have a relation X is much larger than Y, then this would be a definition of the fuzzy relation between the two elements. So 0 is of course not much larger than itself. 1 is not much larger than anything else in this domain. Nothing is much larger than 5, so we get the zeros here. But more interesting, so 3 is much larger than 1 to a degree of 0.4, but not larger than 3 or 4 or 5. And 4 is now the case that we look into in more detail. So 4 is much larger than 1, a little bit much larger than 2, a tiny little bit more much larger than 3, but not much larger than 5 or 4 or 5. And so this is the meaning of this table to the left-hand side. And then we have sort of a closeness relation, and that basically is telling us that 3 and 4 would be very close. 4 and 4 is of course 100% close, and the bigger the distance, the less close you are to another number. So 1 is very close to 1. It's not so close to 2 anymore. Almost not close to 3. A little bit close to 4, and absolutely not close to 5. Given this really artificial example, of course. So basically then the relation of the things for 4, if we now want to calculate the question of x is much larger than some number close to z, so that's the composition of the two operators, then basically here is the example for if we want to see whether 4 is much larger than some number close to 4, so we take 4 and 4. What we have to do is to take the is much larger than relation, combine it with the close to relation. So basically what we do here is we have to take the first value and compare it to the first value in this vector. So 0.8 and 1, we take the minimum of the two, that gets us 0.1. We have to take the minimum of this value and this value. We have to take the minimum of this value and this value, and so forth. So we get the 0, 0, 0.1, 0.3, and from this one we get the 0.1. And then we have, from all these values that we get here, we get the maximum, we take the maximum value. So that gives us the value between 4 and 4. And all the other values have been calculated in the same way. So basically, we have composed these two relations to a new relation in this way that it now represents the composition of two relations. So that's the fuzzy interpretation of the notion of composition that gets us from one relation table to another one. And that basically is if you look at the way this is represented, it sort of intuitively makes sense. So 4 is much larger than some number close to 1. But it's not much larger than some number close to 3. And these kind of things are represented now in this as a combination of the information that we have in the two other relations. So based on this, we have now a formalism with which we can represent knowledge that might be considered vague, but we now have an algebra to reason with this, and we can extend it from now to we have this example with binary relations, but this can be extended to multi-valued relations and so forth. The problem with this is that where do we get these fuzzy functions from? And as I said before, you can sort of learn them, train them. Some of them are described. Some of them can be extracted by some approximation terms and so forth. But this is one of the big problems in fuzzy logics, I would say, that the grounding of these fuzzy functions is an important problem to be solved. In fuzzy control, so that you can, if you want to build an intelligent agent that sort of takes vague notions as a description of its perceptions, you can then describe rules such as if the temperature is cold, then change something on your system. And basically the decision procedure then comes down to some reasoning problem where you have to decide on what kind of values, what weighted average do I have, so that at a certain moment in time I have to relate my measurements from this fuzzy input to some output behavior. And this is a very, very fruitful application of AI technology. It's particularly big in Japan. So many of their Japanese people are often very enthusiastic about technology. So there's a really robots at home kind of philosophy I've heard. Do we have any Japanese people in the room now? My favorite question from the first two, please. Japanese? No? Yeah, you raise your hand. No, okay. Good, because that makes it easier to talk about something I don't know anything about. So, but this technology is really applied in many, many different applications, such as washing machine, elevators, cameras, brake systems. So where you describe the terms, where you can now say, okay, this is now a dangerous situation, so now I have to take an action, but you want to combine sort of several vague terms, and for that you now have a formalism that does this. So to conclude the part on fuzzy set theory and fuzzy logics, it's a flexible formalism. It comes with a formal, with a well-defined, well-specified language that is that partially can be you do in compositional way, but you can extend it with more suitable operators from the fuzzy domain. If you apply it to some propositional language, and you have the crisp sets, so you only have tall people and small people, and you know exactly who belongs to which class, then the semantics that I've given you now with the fuzzy set theory is exactly the same as the semantics based on the truth model theory that we've discussed the last 3 days. So that's very nice. So you get the same results for the same problem if you have it. And it's popular, and it's more used than we might think it is. Problem is, what are the right operators? What are the right functions? Where do the numbers come from, as I mentioned? And it's very important to keep be very clear about what we are dealing here with. So that all we describe is some notion of approximation of a concept, and as soon as we start sort of learning from data about what is tall, what does it mean, we also get some kind of notion of uncertainty into this approximation, and that philosophically and really blurs this a bit and makes it more difficult to really understand what's going on, and whether the fuzzy functions that you learn from training and from data, whether that's valid and so forth. That's something you really have to take to be very careful with. So that's all I wanted to say about the concept of vagueness. The one that has bigger impact and is really the one that is sort of one of the hot topics at the moment because of all the statistical learning approaches and so forth, is the formalisms that deal with uncertainty. And the question is, of course, how can we represent uncertainty with probabilities, because this is the approach that's nowadays standard. How can we reason with this represented knowledge? And then sort of how can we combine probabilistic knowledge in a more efficient way so that you can scale it up a bit in a bigger decision process. And then, as I said, if I find the time today, I talk about the exam and the final project, otherwise we do it on Monday. So there's still 5 minutes to sort of start the introduction part of dealing with uncertainty. And so let's take the extreme case of the automated car or an automated taxi. The performance that you need, the task that you have is to get a flight, and the environment on which to perform is on the road. So we have a non-fully observable environment because we don't know yet what happens on the streets, and we can't see all, we can't put it all on the map. It's multi-agent, stochastic, and continuous. And then the question is, what can a logical agent really do in these situations? Can we say, okay, when we are now on the A10, it is that time, and I know that this is a cross point, so you have to take the steering wheel to the left or the right. There are so many uncertainties in this scenario that this is simply not working. So it works for scenarios that are complex enough, like Schnapsen, where you have a game and you have a decision to make between 5 cards, and you have knowledge about the strategy and so forth. So in that sense, it makes sense. But in these really complex environments, you really need to be able to also quantify the chances of a certain action might have an effect on, and so forth. There are different reasons why we have this uncertainty. Partially, the measuring is simply not reliable enough. So what can you measure in total with a car? If you have a car, even if you put 100 measurements on it, so where you are, how wet is it, what is the wind, and so forth, you will never have the complete knowledge that is needed to get all the inputs that might impact on your decision for your intelligent car. So that's unreliability might be that you think that you have information, but you don't get it because it's broken. Incompleteness means that you don't get the information, or there's too much of it. So like in Schnapsen, we might have, in theory, the complete way of representing the whole belief state, but there are too many of those, so we need to make decisions. And there's also imprecise information, so we sort of need to understand how to deal with this information when we're not exactly sure what in which state we are or what the nature of the state is. Here is an example from the book of Russell and Norvig, and I will add the chapter on uncertainty from the book also to the reader. I don't know whether you saw that I edited the chapter about first-order logic to the schedule of week 2 because the first-order logic wasn't covered in the reader. So now there is an additional chapter for the about this material on this this website on this Canvas site. So maybe as a sort of side comment, I always try to post the material that's useful for you to study on this schedule and material of week 2 Canvas page. So if you haven't recognized that, have found that, that's also where the videos are and the slides are and the exam material. That sort of is for me the place where I put all the material in a concise way. And there also I placed the reader for the first order logic, and I will also place some material on the probability. An example that Russell and Nordic give here is that you have a toothache. So this suggests in a way that you have a cavity, which is a hole in your teeth. I don't know why they use this sort of horrible example, but I have to go with this in this presentation. So one way you would think of representing this would be to say, okay, I have a toothache, so I have a cavity. But that's obviously not a good, valid way of modeling this. It's wrong because not everybody who have toothache also have cavity. So there's no way to pose this as a valid axiom in your knowledge base. So maybe you should write, if I have a toothache, then I have either a cavity or problems with gum, or I have a nosebleed. I don't know what. So you could list all the possible reasons for having toothache. But obviously this doesn't work either, because we would never have a complete list of all the possible reasons for having toothache, either because we are too lazy to write it down or because it's simply impossible. So in many of cases such as this diagnosis problem, when you go to the dentist, the propositional logic or even the first order logic way of writing this down is not sufficient. So here we have a problem. So it's infeasible. Would it work the other way around, that if I have a cavity, then I also have toothache? And of course, this doesn't work either, because you can have a hole in your teeth without even noticing for at least a long time. So this is not a valid way of sort of relating the two problems with each other. But how do you do this in a way? Because this one is wrong again. So here, propositional logic and even first order logic are not sufficient. So we need other mechanisms. There have been some sort of more historic ways of dealing with this. So you have a notion of certainty, and you try to make compositional semantics out of a notion of certainty factors. That was applied in the early years of AI and was pretty successful. So, but I don't want to get into the details of that, because nowadays I think the established formalism is simply probability theory, and I'll go into that after the break. So there's one other way of sort of more dealing with this in a logical paradigm, in a symbolic logic paradigm, and that is default or non-monotonic logics. So you always assume one thing to be true. So I never have to sort of model the information that my car has a tire when I want to go from here to the airport. So I always sort of only look at the normal cases. And only if something breaks down, I need to get extra information. So that would be default logic. And the same would be in the more, you get a non-monotonic behavior. So you can entail things until the moment where you get new information, and then the things that you have entailed, they are not valid anymore. And that is a very difficult thing to treat with in logical paradigms, but sort of that's far outside the scope of this class. And again, the question is not easily answered. What are the assumptions that are reasonable? How can we deal with the conflict that you get automatically? So you have an assumption at the moment, you get a measurement that your assumption was wrong. How do you deal with that? What you do with that? Okay, so then you could sort of apply a more fuzzy-like approach, I would say, so that you say, okay, if this is now the sort of the car example. Something gets me on time to a certain degree, some number associated, some trust associated, some confidence associated with the rule system. if the sprinkler is on to 99% of the cases, the wet is getting the grass is getting wet. This is also sort of natural in a way we do this, but this is really lacking a formal mathematical framework so that we can confidently talk about this concept of predictable inference, so that if we give twice the same information to a system, it will do twice the same decision on this information. So, and in particular, I mean, this might work in the naive case where you have simple rules with weightings, but as soon as you start combining things, the meaning, the semantics is completely unclear. So, as I said before, there was a sort of historically grown method is certainty factor models. That is something that was the basis of the old Meisen system, one of the most successful AI expert systems from the last millennium, I have to say now. It's easy to apply, it's very efficient, but it's hard to justify theoretically because it has no sort of formal basis. And where we now really mostly do work with is probability theory, which is sort of the underlying motor for statistics and machine learning nowadays as well. So we get into that, I would suggest, after the break, and then I sort of explain some things about probability. So let's see you again at 12.